So this video is going to help you answer questions 6 through 14. Our focus question for these questions is how do light waves behave when they interact with matter? And so we're going to watch a video. We're not going to watch the whole thing, but just a snippet of it.
You are so immature.
Come on, Mia, lighten up. You gotta admit that shadow scared you.
Who wouldn't be scared by a giant hulking creature with huge claws?
This itty bitty thing.
It is kind of cool how you made its shadow look so big.
Yeah, it's because of the way light works. When light shines, its waves travel in a straight path.
Waves? I don't see any waves.
Light is made up of waves, but we don't see the waves. We just see, well, the light.
Okay, so the light we see travels in a straight path.
Until it hits something. When a beam of light hits something it can't pass through, a shadow forms where the light is blocked.
So when you held that thing in front of the flashlight, it blocked the beam.
Right, and the light that wasn't blocked kept traveling until it hit the wall.
Look, the shadow's bigger when the creature's closer to the flashlight. Of course, it's blocking more of the light.
Light's used for a lot more than just playing tricks. Light is actually a form of energy.
Really?
Yup, we couldn't live without light, especially from the sun. Light gives us energy and keeps us warm, and plants need it to grow. So check it out. Most light sources, like the sun and light bulbs, give off white light.
That goes for flashlights too, right?
Yup, but inside that shining white beam, there are lots of colors, each with different wavelengths.
How come we can't see them?
We can, but we need a prism to do it.
Sweet.
The prism breaks up the light into 7 colors called the light spectrum.
Looks like a rainbow to me.
Exactly. Raindrops can work like prisms. When you see a rainbow, it's because lots of raindrops are spreading the spectrum of colors across the sky.
So how come when light shines on things, it doesn't make them look rainbow colored? I mean, leaves are green, flowers are pink and yellow, and my hair is blue.
Can't deny that. Okay, here's what happens. When light hits something, like a leaf, special chemicals called pigments absorb some colors and reflect others. The colors we see are the ones that are reflected.
Wait, you're saying that a green leaf absorbs every color except green?
Weird, isn't it? And even weirder, objects that absorb all colors look black, and ones that reflect all colors look white.
Bizarre.
Do you want to hear bizarre? Visible light, the light we see, is only part of the whole range of light waves that make up the electromagnetic spectrum.
Does that mean there are different kinds of light?
Yup, different wavelengths, actually beaming down from the sun and other sources too. Some, like X-rays and ultraviolet light, are shorter than visible light waves.
Ultraviolet light? Isn't that what causes sunburns?
Right, also known as UV. Other light, like radio waves and microwaves, are longer.
Come on. There are light waves in my microwave oven?
High-frequency ones. When they hit your food, they make the molecules inside bounce around and heat up. That's how the food cooks.
Pretty crazy, this light stuff. I mean, it travels in waves. There are visible ones, invisible ones, sun scorchers, even food fryers, and they all make up the electromagnetic spectrum. Then there's the color spectrum inside of that. I always thought light was white. How cool that you can use a prism to separate the waves into all 7 colors of the rainbow, and an object's color is determined by which light waves it absorbs and which it reflects. How weird.
Totally. But that's nature for you.
Well, not even nature can explain why you'd wear a puke green shirt like that.
Hey, it reflects my colorful personality.
Okay. So I lied. We did watch the whole video. And while some of it was a review, some of it was new information, which we're going to go over. So, in summary, which you need this because it's one of your questions on your Google form, light travels in waves. The electromagnetic spectrum is made up of visible and invisible light waves. The visible spectrum, known as the color spectrum, contains 7 colors: red, orange, yellow, green, blue, indigo, violet, revealed when light passes through a prism. And the color of an object is determined by which light waves it absorbs and which it reflects. And we'll talk more about that. So the next slide, I have a lamp. And I want you to think about why this lamp is built to include a lampshade. What is the structure and function of the lampshade? Well, the lampshade keeps the light bulb from blinding your eyeballs, right? And that's because the lampshade does a couple things that sound does. Okay? Just like sound, light can be reflected, absorbed, and transmitted and refracted. Well, that lampshade is absorbing some of that light so it's not blinding us. And it transmits a little bit of light so that we can use that light to see our surroundings. All right. So, like I just said, like sound, when light waves interact with matter, a few different things can happen. They can be transmitted, reflected, or absorbed. Usually, the interaction includes a combination of some or all of those options, depending upon the material that the matter is made up of and the frequency of the light waves. You're going to see a chart to the right with actually 6 different interactions, but we're only focusing on these 4: transmission, reflection, absorption, and refraction. And so, really quickly, let's review some vocabulary that you should have learned in elementary school. So, there are 3 different kinds of objects: translucent, transparent, and opaque objects. Transparent objects, you can see through them, and it allows all light to pass through. Translucent objects, you can kind of see through them. An example of a translucent object would be like a frosted glass window versus a transparent object, which would be a window. And then an opaque object, no light can pass through. And an example of an opaque object would be like a door, a wall, or a book. Okay. So let's investigate absorption. We'll come back to color vision. I'm going to walk you through these next 2 slides. We'll talk about color vision, and then we have a quick video we're going to watch. So the color of an object is the color of light it reflects. Objects in white light. Unless an object emits its own light, like a light bulb or a colored light bulb, an object has to reflect some light in order to be seen. When you look at a wall, since it does not emit light waves, it is reflecting some light in order for us to see it, but also absorbing other light waves since it is opaque. Depending upon the visible light waves that it reflects, we will see it as a specific color. If you saw a red wall, it would be reflecting the light waves with the frequency to appear red and absorbing the others. The plant on the right appears green because it's reflecting green light and absorbing all the other colors. Now, objects in colored light is different. So objects can look a different color depending on the color of light in which they're seen. The picture below shows 4 photographs, each taken under a different light. The first picture was taken under a white light. In it, the card is red, or the hearts are red, the berries are blue, and the pepper is green. The second, third, and fourth pictures were taken under a red, green, and blue light, respectively. Let's take a look at that third picture. So when green light shines on an object, any object, the object is either going to reflect the green light or absorb it. Okay? Which object here is reflecting the green light? Well, the card, the white part of the card, and the pepper itself, because the pepper is green. Since red objects, so the red hearts, and blue, like our blueberries, only reflect red and blue, they absorb all of the green light. And this is why the hearts in the third picture look black, and why in the fourth picture they also look black. This is true for the second and fourth pictures as well. So, objects or materials are considered to be transparent, translucent, or opaque, depending upon how light behaves with them. Transparent objects allow all the light to transmit or pass through. Translucent objects scatter the light as it passes through. And then opaque objects absorb light waves as they hit it. Now, all three of these objects or materials that are considered to be transparent, translucent, or opaque, they all have to reflect sunlight in order for us to be able to see it. So understanding absorption.
Hi, I'm Becca Emringer at Edmund Optics. Today, we are going to absorption and reflection of light, and the reason we see certain things as certain colors. Absorption of light occurs when an object absorbs certain colors or wavelengths of light, not allowing the light to be either reflected or pass through the object. Some objects, like this matte black photography paper, absorb all wavelengths of light and reflect no colors, such as red, orange, yellow, green, blue, or violet. Other objects, like this white table, do not absorb any visible wavelengths of light and reflect all of the colors to create white. In most cases, objects will absorb a portion of light, meaning that some wavelengths will be absorbed and others will not. Let's demonstrate absorption of light by using a flashlight and different colored filters. Remember, the light from a flashlight is white light and contains all colors of the spectrum. Let's start with this green filter. When we shine the flashlight through the filter, only green light passes through. All of the other colors, including red, orange, yellow, blue, and violet, are absorbed, leaving only green to pass through. Now, let's take a look at this line. Colors such as red, orange, yellow, blue, and violet are all absorbed. Only the color green is reflected, which is why we see that color when we look at the line. Knowing that filters absorb light, let's think about what would happen if we shine white light through all the different colored filters. What do you think will happen? Can you take an educated guess? Remember, white light is made up of all the colors of the spectrum. If you guess that no light will pass through because all of the visible wavelengths of light are being absorbed, you are right. Now we'll have some fun and demonstrate absorption of light using gummy bears and lasers. Here I have a few green gummy bears and a few red gummy bears. I also have a green laser and a red laser. When I point the red laser through the red gummy bears, the red light passes through. When I point the red laser through the green gummy bears, the light does not pass through. This is because the red light is absorbed by the green gummy bear. Let's try the same experiment using the green laser. When I point the green laser through the green gummy bears, the green light passes through. When I point the green laser through the red gummy bears, the light does not pass through. This is because the green light is absorbed by the red gummy bear. You can practice your knowledge of absorption of light wherever you go. Just remember that we see objects as the colors they are because colors from light that you can't see are absorbed, and colors you can see either pass through an object or they reflect off of an object. Check out edmundscientific.com for more fun videos.
Okay, so that was all about how light is absorbed when it comes into contact with transparent, translucent, or opaque objects. Now let's talk about reflection. So in this simulation, I'm going to do a couple different things, and I just want you to think about like what you see, like what do you observe? And if you look at the link above, you can type that link in. I feel like if you just type in bending light and FET Colorado into Google, this should pop up. So you can play around with it. So what we've got here, the top of the screen is air, and the bottom of our screen is water. And if I turn this laser on, what do you think is going to happen to the light wave? Well, you can see here that when the light hits the water, some of it gets reflected, some is going to be absorbed at the surface of the water, and then most of it is going to be transmitted. And there's a lot going on here. So this light wave, while it's straight, as soon as it hits the surface of the water, it reflects to the right, and then it goes through the water, but notice there's a bend here. There's a little bit of a bend. Okay? So I want to focus on what's happening up here at the top, though. So what you should see is that not all light is reflected. Some of it is absorbed. What does it mean when a light wave is reflected? Well, when a light wave is reflected, it means that it is bouncing off of a surface. When light is reflected off of an object, there are two rays. The incident ray is the original or incoming ray, and the reflected ray, which is the one that bounces off. So here is our original, our incident ray, and here's our reflected ray. And there's something that's true about these. There's a pattern here. So I'm actually going to pull out our protractor and I'm going to line this up. I'm not a math teacher, so I don't know these terms. Like when this line comes into contact with the surface, like what do you call all these congruent lines? I don't know. I'm not a math teacher. But what I do know is that if I line the protractor up with the surface of the water and the angle at which the light meets the surface, we can learn something about the original ray and the reflected ray. If this is coming in and it looks like it's a, let's see, 40, 50 degree angle here, the reflected ray is going to reflect at the same angle and be 50 degrees as well. Maybe that's not 50. Maybe that's 45. It's a 45-degree angle. Okay. And I feel like I can change this. If I change this to 60 degrees, look what my reflected angle is. It's 60 degrees. If I change this to 30-degree angle, if my incident ray is 30, then guess what? My reflected ray is also 30. Okay? So, what pattern exists when light waves are reflected off of a surface? Well, the angle of incidence is equal to the angle of reflection. Now, all kinds of electromagnetic waves reflect. So microwaves reflect, radio waves, gamma rays, infrared rays. They all reflect, not just visible light. But investigations like this can help us try to explore reflection in a visible way. The relationship shown in this investigation, the angles of incidence and reflection are that they're equal. This is known as the law of reflection. The law of reflection is useful because it represents a pattern, and that pattern can be used to make predictions about what will happen when all kinds of waves are reflected. So it is not just true for EM waves either. This is also true for mechanical waves, like water waves reflecting off of the side of a pool or sound waves echoing off a cliff. If light waves reflect off materials, like books or the sides of brick buildings, so that they can be seen, why don't we see our reflections in them? So if light bounces off of a wall back to us so that I can see the wall, why can't I see myself? Because light bounces off of me and bounces onto the wall and then bounces back. So why don't we see ourselves? Well, in order to be able to see our reflections the way that we do in a mirror, light waves have to reflect off of a very smooth surface so that the waves reflect uniformly enough to maintain an image. Most of the time, light waves reflect off surfaces that are not smooth, like a book or a building. The surfaces of most objects are bumpy enough that light rays reflect at many different angles, and they can't maintain an image. Think of looking at your reflection in a pond when the water is smooth. As long as the water is smooth, you're going to be able to see it. However, if someone drops a stone in the pond and causes many small waves so that the surface of the water is no longer smooth, your reflection will be distorted or you might not be able to see it at all. This is because once the water is no longer smooth, the light waves are reflecting in many different directions at once. So here's an example. The picture on the left shows a mountain reflecting off of the smooth water surface. This water is so smooth that the light waves reflect off of it just like a mirror. And so you can see the reflection of the mountain. But on the picture in the picture on the right, this water is really wavy. And so when the light bounces off of that rough water, it scatters and it can't maintain an image. And so you can't see this mountain being reflected very well in this pond of water. Okay, so refraction. Let's go back to our simulation. And this time, we are going to use a prism. And I'm going to turn on this laser. And the light's going to go straight through. But if I change the angle, notice what that light does. It bends because it's going in at an angle. See the light bending? See that? It would do the same thing if I put a, oopsie, that's because I got this in the way. Let me get rid of that, okay? And then I can turn this. So notice what happens when I use a prism. If we go back to our simulation, our first simulation, you can see it happening here. So when the laser hits the water, notice it's not a straight line. It bends a little bit. And we call this refraction. So when a wave changes from one medium to another, the wave bends. And this is called refraction, and it is a result of a change in the wave's speed and direction. White light entering a prism is bent or refracted, and this will actually separate the light into, I don't even think that's the right word. It's constituent wavelengths. Maybe it is. So if I pull this back up, let's get rid of this. Put that back. Okay. At school, we had prisms for you to be able to try this out. It's a really cool lab. But I'm going to make this a dark room. Make this dark room. And I can't move this, but I can turn this. And you can see that when you shine, oh, there it goes. That was good. Right here. When you shine a white light through a prism, because of the angle it's entering, it changes the direction and the speed. And you can actually separate using a triangular prism or even a rectangular prism. You can separate white light into the colors of the rainbow. And so you can kind of barely see here. We've got red, orange, yellow, green, blue, indigo, and violet. And you can see it down here really, really well. And then also depending on where it hits, there's a really good picture of it, okay? And here's a good picture of it too. But each wavelength of light has a different color based on the angle at which it bends. But just know that you can, when light does go through an object, depending upon the shape, light will refract or bend, and you can actually separate white light into the visible light spectrum, like the colors red, orange, yellow, blue, or red, orange, yellow, green, blue, indigo, violet. And then the colors of white light will always emerge in that order. The order will never change because of the frequencies, the wavelengths. And so I've got a video for you to help understand what refraction is. There were so many cool labs that, and you know what? I don't think I'm going to be able to click on it because that's in the way. Oh, there it goes. There we go. Hopefully this is more helpful than my demonstration.
Hi, I'm Becca, the Educational Outreach Manager at Edmond Optics. Today we're going to talk about refraction of light. Refraction is when light bends when it travels from one medium to another. A medium is any substance. Here I have a glass of water and a popsicle stick. I'm going to insert the popsicle stick into the glass of water. As you can see, it appears that the popsicle stick bends at the barrier between the air and the water. Refraction is caused by a change in the speed of a wave of light when it moves from one medium to another. Just imagine if you're riding your bike on pavement and suddenly cross over to sand. Your bike is going to slow down when you move from the pavement to the sand. The same thing happens with light. When light hits a more dense medium, the light wave is going to slow down. When it hits a less dense medium, it's going to speed up. The same thing happens when I put this lens in front of my face. The light slows down and changes direction or refracts, making my eye appear smaller than it actually is. Now let's look at a ray of light traveling from a less dense medium, the air, to a more dense medium, the water. When the laser light travels from the air and hits the water, the light slows down and refracts. If refraction did not occur, you would expect the beam of light to travel in a straight line. But since the light slows down and refracts once it hits the water, it bends from its original course. Here I have a large beam of light traveling through a fish tank. When I put a lens in front of the beam of light, the light will refract. When I move the lens further away from the light source, the light will refract to a point. In most cases, when light waves speed up or slow down, they change direction. I am shining laser light through an optic. The laser light is starting at 0 degrees, but when it hits the optic, it slows down and slightly bends. The laser light then comes out at 4.5 degrees. So now we know that refraction is the bending of light, and that light travels more quickly through less dense materials, and it travels more slowly through more dense materials. Good scientists and engineers always test out scientific theories for themselves. To find instructions for these demonstrations.
All right, I think she did a much better job of explaining refraction than what I did with the simulation. So, how do light waves behave when they interact with matter? Let's sum this up.
Can you hold the tripod steady, RJ? I want to get that white egret before it flies away.
I'm trying. This dock's a little rocky.
Oh no, now the sun's in my eyes.
Yeah, look. The sunlight's reflecting right into the camera lens.
Why does it always do that?
Well, light travels in a straight line, right?
Yeah, I know that.
So when it hits smooth, shiny surfaces like water or metal, a mirror image of the light source is reflected or bounces off.
And ends up over here? How?
Simple. Angle in equals angle out.
Angle of what?
The angle of incidence. It's the angle at which light hits a surface.
That makes sense. Incidence. For the angle light comes in.
And out's the angle of reflection. The angle at which light bounces off a surface.
Reflect means bounce off. I get it.
So when light hits smooth, shiny surfaces like water, it reflects off at the same angle it comes in. The angle of reflection equals the angle of incidence.
Gotcha. That means if we check out the angle of the rays, we can move the camera so the reflection doesn't hit us.
Brilliant thinking.
Here, this works.
Oh no, there goes the egret.
Well, maybe it'll come back later. Let's get some shots of that funky red boat. The color's really good.
Yeah, and no reflection.
Why's that?
For 2 reasons. First, remember what we learned about light and color in class? When light hits a surface, some of its colors are absorbed, taken in, and not reflected.
Oh yeah, and we only see the colors that are reflected, like the red and yellow on the boat.
Yep, but also the boat has a rough surface. Unlike water, which has a smooth surface that reflects most of the light, the rough surface diffuses the light. That means it sends it in many directions.
And since the light doesn't reflect in just one direction, there's no mirror reflection?
Exactly.
Archie, look! Is that rope bending?
The rope's not bending, but the light is.
Come on, how can light bend?
When light passes from one substance into another, like from the air into the water, the light waves will bend. Instead of being reflected, the light waves hit the water, bend, and travel downward. It's called refraction.
Weird.
But true. The light bends right at the point where it leaves the air and goes into the water.
I gotta get a shot of that.
Nice!
Wow, light's got so many cool qualities. Light that's reflected changes direction when it bounces off a shiny, smooth surface like water or a mirror or even metal. When it does, the angle of reflection is the same as the angle of incidence, the angle at which the light hits. And light that's refracted is bent as it passes from one substance into another. Refracted light makes objects look bent. And last of all, light can be absorbed or taken into a substance, and that affects the colors we see. I think all this light stuff will help me take even better photos.
Well, you better snap to it. The egret's back.
Oh man, I gotta get this, a reflected refracted action shot.
All right, and that's it.